very much. It's a real pleasure being here. This presentation is divided in 5 stages, and I'm going to start by talking a little bit about our motivation and why this work was important for us. So, as the environmental and energetic needs of our planet call for turning away from fossil fuels, there's been a growing interest in research and society for clean and renewable energy sources like nuclear fusion, for example. Here we can observe two stellarators, the Wendelstein 7X and the SCR1, which are plasma confinement devices. These are helically symmetric toroidal tubes surrounded by solenoidal coils that generate a magnetic field that it can be used to influence charged particles, or say, for example, atoms of hydrogen that can then fuse into helium, and this can be used to generate energy. But the actual assembly and design and testing of these machines is quite complex and expensive, which is why it is crucial to rely on computational simulations. Now, the simulations are no free lunch either, right? They are complex, and you often rely on vast amounts of calculations over lots of data. So this is usually done on high-performance computing systems. This typically follows the message passing paradigm, where we have some sort of message passing standard like MPI for distributed memory parallelism, and then we have another model X that handles intranode parallelism. So there's been a widening diversity in computer architectures. So this X model can be tons of options depending on our architecture, and this also has another effect, which is that different memory access patterns and different data layouts suit better different architectures. So take for instance this image where we have some GPU memory access patterns, and we have lines of contiguous memory represented as the rows there, and we can see these lines, if we need to access them, they need to be completely loaded, even if we are only going to be using part of these lines. So if we use a coldest access pattern, where each thread would access some portion of these lines, we would only need one load operation. Whereas if we use the blocked access pattern on the right hand side, where each thread accesses a different line of memory, we will need one load operation for each of these lines. So this is computationally expensive, and this decision can have a big impact on the performance of our applications. So for this reason, it is desirable to be able to program these simulations on a performance portable manner. And what we mean here is that we can reuse the same source code on a wide variety of architectures without sacrificing much of our performance. There's been a number of performance programming models and frameworks designed for this, and so the idea is that they are able to abstract these different parts of the code, like the memory layouts, regardless of if we are using the CUDA space, the heap space, or if we want to use CPUs, or whatever we decide or we have available in our architecture. So previously, as part of the design of the SCR1 stellator we saw earlier, our team developed the BS Ultra, or Biot-Savart solver, for computing and tracing magnetic field lines. And this was originally designed to run on CPUs, and the data layouts were the ones we have on the left-hand side here. So we had basically some structs of arrays, where we have 3 arrays representing the coordinates or spatial positions of each of our structures. And this work was then continued to port it to GPU, and for easier data transferring between devices, there was a decision made to convert all these data structures into one-dimensional arrays where each 3 spaces have the information of each single particle or coil and every data structure represented. This change helped us to obtain a speed up of over 5 times, which at a first glance sounds pretty great, but there's a catch. When we ran the new code variant on CPUs, we had a 6.7 times slowdown relative to the original results we had on the original version of the code. So this led us to notice that there was something off, and we decided to develop a performance portable version of this code. To get a little bit into the details of what this simulation does, this is basically a field line tracer that was developed on OpenMP originally. And we basically represent the coils as a sequence of straight lines or filamentary segments, which can be used to calculate the magnetic field at every point in space. And this magnetic field can be used to approximate the trajectories of the particles, and we did this with a Runge-Kutta fourth order algorithm. In addition to this simulation to explore other representative HPC plasma physics simulations, we also decided to adapt particle in cell, and for this we decided to use the parallel research kernels PIC, which was also developed in OpenMP. And the simulation basically represents a two-dimensional grid with charges on its mesh points, which are the green dots here. And in each iteration, these charges exert forces on the particles of the four surrounding cells. And in return, each particle it also affects the charge of the mesh points of the four neighboring mesh points of each particle, right? So this simulation also offers different initialization patterns for particles to induce some load balancing scenarios, but we are focusing on the X intranode parallelism models, so we should expect that different load balancing scenarios shouldn't affect our results. Now, to measure how performance portable our new implementation was going to be, we decided to adopt Pennycook's performance portability metric, which considers a set of platforms, which are the devices we're going to be running our code in, an application that solves a problem. So we have our code variants that solve either the field line tracing or the particle in cell, and we also have the efficiencies of these applications. Now, there's a number of ways on which we can measure this efficiency, but we decided to use application efficiency, which basically means that for each execution, we define our efficiency as a fraction of the best observed, the performance obtained as a fraction of the best observed performance on each platform. Now, to develop our new code variants, we decided to use Cocos because in the literature it had proved to obtain some of the best performance portability results and some of the widest varieties of hardware. And Cocos offers something which is very valuable, which is the Cocos views, which are an abstraction of the data structures we want to use, which basically lets us define an execution and a memory space during compile time. So I can program my code, my data structures, store them in a Cocos view, and during compilation I can hint the compiler if I want to use a CPU, a specific CPU, or a specific GPU, and if I want to use the managed memory alternatives like CUDA, UVM space, or heap managed space. So Cocos gives us this, and we decided to do a full porting of PS Ultra, changing every one-dimensional array into a Cocos view. And then in the peak, we had the particles represented as structs with coordinates, velocities, accelerations, charges. So we decided to keep these structs and store them in Cocos views of these structs. So to run our covariance and test them, we used the CARLA supercomputer in Costa Rica, the Rica supercomputer in the Max Planck Institute in Germany, the AMD Accelerator Cloud, and an NVIDIA Grace Hopper machine. So we had GPUs from NVIDIA and AMD, and CPUs from Intel, AMD, and NVIDIA. So for our results, we have on the left-hand side our CPU results, and on the green line here, we can observe the original time durations of the VSL execution. And this green line is the CPU-only version that was optimized for only CPU, and we can observe that our Cocos version on this line is about 2.5 times slower, which is way less drastic than the 6.7 times that we had previously uh, obtained with when we did the porting. On the right hand side, we can see that on the older V100 and A100 GPUs on these lines, Cocos, our Cocos code variant was not as good as the OpenMP version, but this difference was then settled on the MI210 GPU and on the newer MI300 and H100 GPUs. This was the other way around, where we have Cocos performing better than the OpenMP variants. We also decided to test how these program code variants would scale. So we used up to 16 GPUs, and we did two experiments. Our strong scaling experiment on the left-hand side basically means that we have a particle count or a problem size, and this is evenly distributed between the GPU counts we have. So we should expect that double the GPUs would achieve double the speedup. This is represented in the ideal dotted line here. And we can see that in our largest problem size, we were close to this, but the reason why it is not ideal is because these problem sizes were not large enough to saturate all the GPUs we had at the moment. And on the right hand side, we have the weak scaling experiment, which means that our problem size scales with the amount of GPUs in use. So if we have 16 GPUs, each one of those has this amount of particles, for each problem size. And as there are no deviations in any configuration, we have ideal weak scaling here for both our Cocos code variant and the previous OpenMP code variants. So when we measure the application efficiencies of these results, we can observe here that when Cocos was outperforming OpenMP, the application efficiencies obtained by OpenMP were not were quite low. We have these 61, 57, and 37% of application efficiencies. And using these application efficiencies on the Pennycook's equation we saw earlier, we obtain these results. Now on these platforms that only takes into account the GPUs used, we observe that the OpenMP baseline code variants only achieved 78% of performance portability. And when we include the CPU we used for this experiment, it goes down to 66%, while Cocos never fell below 96%. Now, on the particle and cell results, we have the CPU results on the left, and we have Cocos with a crosshatch pattern, and we can observe that on the CPU, the results were better for Cocos on both CPUs tested. And then on the right hand side, we have the GPUs, and we can see that for the V100, Cocos was better, but with the A100, it was the other way around, but the difference here are very slight. So again, when we calculate the application efficiencies of these results, we again see that for some devices, OpenMP got quite low application efficiencies, like this 64% or this 72% here. Using this on the performance portability metric, we again get some low results for OpenMP with 67% on the CPUs and 80% on all the devices considered. So basically, we obtained some very performance portable versions of our code with Cocos, with both simulations never falling below 96%. And we also observed that on the newest architectures, Cocos did seem to obtain some of the best results. And it's important to keep in mind that this kind of study is quite important to observe how different problems behave with different hardware and different programming models. But many times when we have to develop a big code base, we won't have the chance to to develop multiple code variants, and so we won't be able to measure the application efficiencies of these code variants. So for this reason, we consider that future performance portability studies should focus on performance modeling, and of course there's some further optimizations and explorations that we can do on our code variants to obtain some more detailed results. But this is what I was going to show today, so thank you very much.
Thank you for this great job and great presentation. I just have a few more detailed questions, understanding everything correctly what I saw. And you said you're using OpenMP on the GPUs. I guess you're using the target construct to work that. Because like, in our experience, this is kind of relatively new, and the runtime services are quite new, and they're even sometimes buggy. So it's not surprising that the OpenMP results on GPUs are lower or something. This was a comment, not a question, sorry. The second one was more, I guess you have it in your paper, but you didn't say anything about how the compilation, like how do you make sure that on different platforms you kind of use the same level of compiler optimization codes and stuff like that? Because I mean, just by changing some compiler optimization levels, you can get already different speedups, yeah. And so the additional complication, and you want to compare different compilers on different systems.
Thank you very much for the question. That's actually interesting because in our Cocos code variants, in our compiling, we do specify which architecture we are going to be using. And Cocos handles most of the optimizations. Like we didn't go too deep into this compiling with Cocos. While on the OpenMP baseline versions from our previous work, we did use the flags that are like the compilation flags that are special for OpenMP and its optimization, especially on the CPU baseline version where we had the best CPU performance with DS Ultra. That one used special vectorization instructions for AVX 512 instructions, and so that makes that gives some better looks into Cocos.
Thank you.
Thank you.
Thank you for your presentation. It was really interesting. I have a question regarding the metric of application efficiency. Is it proposed by your paper, or it comes from somewhere else?
No, the application efficiency metric also was proposed by Planck and his work, where they proposed the performance portability metric. They also proposed other metrics. We wanted to explore architectural efficiency, which considers like the theoretical peak performance achievable by each device. But this was complicated because it doesn't seem to be standardized when the vendors tell us how many flops their devices or their CPUs achieve. So we have actually been exploring on performing like benchmarks that help us set what our architectural efficiency theoretical peak would be. So yeah.
Thank you. Well done.
Thank you.
Okay, let's thank the speaker again.
Me dejaron preguntar.